this lesson, we're gonna focus on curvilinear motion. Now, I will assume that you have already discussed the concepts of position, distance, velocity, and acceleration in your previous topics. So we'll just cover some important aspects, and then we'll move on directly to problem solving. Now first, for position, if the particle is at a point xyz on the curved path of an arc length s, this is our arc length and this is our particle, then this location is defined by the position vector, which is r equals this length r equals xi plus yj plus zk. And then at any instant, the magnitude of r is the square root of x squared plus y squared plus z squared. Now this is just using the Pythagorean theorem. Now sir, what do you mean by this? Let's say we have a cube. By the way, the components of r are functions of time, and therefore the value of x is x of t, and then y is y of t, and then z is equal to z of t, and then entirely r is equal to r of t. Now what do we mean by r? Let's say we have this rectangular box, and then we'll define this point as our reference point of the x, y, and z axes. Now if I'll draw a line from this point up to this point, notice that it will have a component along y, a component along z, and a component along x. So let's say this distance is 7, and then this distance is 4, while this distance is, let's say, 3, then this distance will also be equal to 4. So this is also 4. And so therefore, if this is r, the length of this line will be the square root of x squared, which is 7 squared, and then plus y, which has a distance of 3, and then we will square this term. And then we have plus z squared, which is 4, so this is 4 squared. And so the length of the line will be square root of 7 squared plus 3 squared plus 4 squared. And so that will be square root of 74. And so this is just the meaning of that. Now the direction of r is specified by the unit vector u sub r is equal to r over r. And so now we'll move on to velocity. Now velocity is the first time derivative of r. To put it simply, if we'll differentiate the function r with respect to time, then we can get the velocity of the particle. So we have, this is the function r. If we'll differentiate with respect to time, we have, this will become dr over dt, and then this will be d over dt of xi, and then d over dt of yj, and d over dt of zk. Now accounting for the changes in both the magnitude and direction of the components of the vector, we can eliminate the first terms on the second equation, provided that the reference frame of the x, y, and z axes will not change over time. Now notice that ijk right here will not change over time. Therefore, it is constant. Now, since we have this equation, we can actually apply the product rule of differentiation, which is uv prime plus vu prime, in order to separate this. And so if we'll use uv prime plus vu prime, we have this expression will now become x di over dt plus I dx over dt. Now, where does this come from? Now, let's say our x is u, and then our I is v. So we have uv prime plus vu prime, in which our u is x, and then v prime, differentiating I with respect to time, that will become di over dt. And then for the second term, we have vu prime. Now our v is I, so we have I, and then u prime will be the derivative of x with respect to time. So that will be dx over dt. So that's where this comes from. And then doing that to the rest of these terms, we can get the following. However, if we will now treat I, j, and k as constants, because they will not change over time, again, I, j, and k will define the reference frame of the x, y, and z axes. So differentiating them, we'll get a value of 0. Because if we'll differentiate a constant term, it will become 0. Therefore, in di over dt, since we are differentiating I, then that will become 0. So this will be 0, this will also be 0, because we are differentiating j. And this will also be 0 as well, because we are differentiating k. And so we are left with the following. And so adding all of these, we can get dr over dt, which defines the velocity of the particle. So we have v equals dr over dt, and then we are left with the following expressions. However, for simplification purposes, let's just put dx over dt first, and dy over dt, as well as dz over dt, before the ijk components. So we have dx over dt of I plus dy over dt of j plus dz over dt of k. And so since we know that dr over dt is just equal to v, let's just change this to v. So we have v equals dx over dt is just vx. So this is Vx, this is Vy, and this is Vz. And so we have this. V equals Vxi plus Vyj plus Vzk. Now if we'll use the dot notation, we now have this. Vx is equal to dotted x, Vy is equal to dotted y, and then Vz is equal to dotted z. Now what this means is Vx is the first time derivative of x, which is a function of time. Now you may just relate this to our notations of derivatives. Recall that if we have a function y, if we'll differentiate this, we have y prime. And then if we'll differentiate y prime, we have y prime prime. And so you may treat the original function as y, and then since this is y prime, in vectors, this will become a dot notation. So we have one dot because we only differentiated once. Now the magnitude of v will still be the same earlier. However, we will now substitute vx, vy, and vz in our equation. And then the direction is specified by the unit vector u sub v is equal to v over italicized v. And then this direction is always tangent to the path. As you can see right here, this line is tangent to our curve because this is our velocity. Now finally, for the acceleration, it is obtained by taking the second time derivative of the above function, which are x of t, y of t, and z of t. And so that's why this already has two dots for the components of our acceleration. Now a is just dv over dt, or simply the change in velocity with respect to time. And then these are our components. Now you may also define acceleration as the first time derivative of velocity. These two are just the same. However, this has two dots because we will now differentiate twice. While this is one dot because if you'll differentiate the velocity function once, you can get the acceleration of the particle. And then the magnitude of the acceleration will be square root of ax squared plus ay squared plus az squared. And then the direction is specified by the unit vector u sub a is equal to a over italicized a. And then since we are talking about acceleration, the magnitude and direction will not be tangent to the path, as you can see here.